So, what factors increase the risk of disease transmission indoors? It's often helpful if we can estimate the level of risk for transmission in a space or situation. This can help us plan out strategies to reduce the risk. However, this is also one of those things that is easier said than done. Most of the ways that we quantify risk of respiratory disease transmission in a space focus on transmission at longer distances when the air is mixed in the room rather than close contact spread. This is because it allows us to think about the risk to anyone in a room rather than just the risk of one person who is right next to someone who's sick. At the room scale, the risk of transmission depends on how many infectious germs are hanging out in the air. That is, it depends on the concentration of the germs in the air. The concentration depends on a bunch of factors. Some of these factors are related to the source of the germs, aka the people, and include the number of people in the room. The more crowded a room, for example, the higher the risk. The activity level in the room, the more people coughing or activities happening that generate lots of particles like talking or exercise, the higher the risk. The likelihood that one or more persons in a room is sick, when there's a higher chance that someone in a room is sick, such as during the flu season, the higher the risk. How long a sick person has been in a room is also important. The longer the time in the room means more exhaled particles and so more risk. Other factors are also related to the germs and particles themselves, such as how long the germ-carrying particles float in the air. The longer the particles are in the air, the higher the risk because it increases the chances that someone else breathes them in. How long the germs can survive outside of a person? The longer germs survive in the air and the higher the risk because, again, it increases the chance for someone else to breathe them in. And still even more factors are related to the building or space itself, such as the size of the room. If we put the same group of people in a smaller room, there's more risk because there's less air to mix the germs into. The ventilation rate for the room. The less ventilation we have, the more risk because we're not flushing out the air as much. Whether there are any additional remediation processes happening. Added strategies like filtration can help remove particles and decrease risk. You can probably see that things can get complicated really, really quickly. So let's try and break this down with an example. To start, let's consider how the risk of disease transmission generally changes over time in a room. Imagine a room with no one inside. Suddenly 10 people come in and one of those 10 people is sick. Everyone is breathing and talking and maybe even occasionally coughing, exhaling particles into the room. Some of these particles might carry germs, and the risk that other people get sick starts to go up. However, ventilation helps to remove some of the particles that people exhale, and some of the particles also deposit on surfaces in the room. This actually reduces the risk. Also, some of the germs in the particles, especially viruses, don't survive well outside of a person, and so they do die while floating in the air, further reducing the risk. Over time, the concentration of particles in the room, including germ-carrying particles, is going to reach a constant amount, and that amount is known as a steady state. We discussed this in the first series of modules. Remember that the steady state is like a maximum amount of germ-carrying particles in the air. The steady state amount of germ-carrying particles is a balance between how fast they're emitted by people and how fast the germs are removed from the room or killed in the room. The time that it takes for the amount of germ-carrying particles to reach steady state depends on how fast they are removed from the room, assuming they are constantly emitted from a sick person in that room. When things are removed faster, a steady state is actually reached faster. But more importantly, if steady state is reached faster, this means that the removal processes are more effective. In this case, the actual amount of germ-carrying particles would be lower, and this reduces the overall risk. This also suggests a natural way to reduce the risk of infectious disease transmission in a room or in a building. That is, we need to remove germ-carrying particles faster. Here we have a few options. Our main choices will be increasing the ventilation rate, or adding or improving filtration, or both. We'll address all of these more in the next set of modules. There's also the potential to try and make the germs die faster while they float in the air, for example, by using special lights that can kill germs. But this is not very common outside of healthcare facilities at this time. A last important factor that affects infection risk is how much time a person spends in a space. Imagine that you enter an occupied room. The longer you spend in that room, the more air that you'll breathe in. This means that the chances that you'll inhale germ-carrying particles goes up. And the more of these particles you inhale, the greater the risk that you'll get sick at all. So the strategies we choose and the importance of decreasing the amount of germs in the air can depend on the expected occupancy time, length, and schedule. That is how much time people spend inside the building and when.